Standard physics typically maps a wave by tracking phase as a simple angle rotating on a flat two-dimensional plane. The A framework models reality as an emergence from a single foundational vibrational field, where mathematical parameters dictate the coupling intensity between physical and informational structures. But tracking these interactions using one-dimensional phase creates a limit. Attempting to map complex multi-axis rotations on a 2D plane results in mathematical singularities. To bypass this, the framework utilizes quaternions, a four-dimensional algebraic system. A quaternion represents a complete, stable orientation in three-dimensional space, maintaining its central reference even while rotating across multiple axes simultaneously. This algebraic choice allows the framework to track field interactions without the geometric breakdown inherent in simpler models. This architecture imposes a specific constraint. Every valid configuration of the field must be positioned on the unit quaternionic manifold. This is defined mathematically as Q being an element of S3, with a norm of 1. Fixing the radius ensures the internal rotational degrees of freedom remain normalized. By operating within this normalized space, the framework can quantify the organization of the field through a quaternionic proxy for phase entropy. A coherent state appears as a tight cluster of orientations. When these points disperse across the manifold, the phase relationships become uncorrelated. The framework calculates the transition between these states by measuring the algebraic dispersion of these points, which signals when a system can no longer sustain a stable structure. Entropy becomes the measurable geometric dispersion of phase orientations across the S3 manifold. When reality is defined by phase-based geometry, the concept of evolution shifts away from objects moving through linear space. Temporal evolution in the A field is driven by the internal rotation of the state, where the partial derivative of Q with respect to time equals omega Q. The physical transformation of a state is represented as a continuous rotation within this internal phase space. Because these rotations operate under SU2 symmetry, the geometric transformations remain continuous and mathematically invertible. The framework tracks the orientation shifts of local phase generators, which differs from tracking the trajectory of a particle in a vacuum. Millions of these local rotations accumulate across the field, with their collective geometric twisting producing the macroscopic changes we observe. The three-dimensional nature of these rotations introduces non-commutativity, meaning the specific sequence of orientation shifts dictates the final state of the system. Time functions as the internal kinematic rotation of phase structures within the quaternionic space. If the field consists of rotating phase orientations, there must be a mechanism to prevent these configurations from dispersing into total entropy. The framework defines a class of stable configurations called reality knots. A reality knot occurs when phase rotations align into trajectories that close back on themselves. These formations create non-contractible loops within the S3 manifold. The phase wraps around the internal geometry and locks into place. This specific topology prevents the structure from unwinding. The rotational paths are knotted and cannot be smoothed out without disrupting the entire system. The stability of this loop is maintained by the local coherence field, which acts as a bounding pressure to keep the knot's boundaries defined. As these microscopic topological knots aggregate and interact, they form the stable networks we recognize as physical matter. Physical persistence emerges as a consequence of topological locks within the phase field, rather than an inherent property of matter. To reconcile this invisible four-dimensional phase space with our three-dimensional observations, the framework requires a bridge. This requires a dimensional transduction operator to map internal phase relationships onto geometric configurations. The framework utilizes the Hopf projection as this mapping operator. This forces the normalized quaternionic states to collapse, projecting their four-dimensional data onto a standard two-sphere. This projection provides the necessary mechanism for internal phase data to manifest as an observable structure. For these higher dimensional phase states to interact with three-dimensional physical variables, they must undergo this reduction to become observable. Projected onto the sphere, the phase resolves into its final observable form, the tetrahedral Merkaba decomposition. The four quaternionic components, A, B, C, and D, map directly to four barycentric weights. These weights define a simplex structure that locks the abstract phase into a stable geometric arrangement. The Merkaba structure functions as a mathematical output, the most balanced arrangement for organizing phase information in physical space. The entire system ultimately moves from abstract non-commutative algebra through the complex topological locks of the manifold to this final geometric mapping. Quaternions provide the exact algebraic mechanism required to map multidimensional phase vibrations into stable physical reality.